Hello and welcome back. We're going to be going into part 2 of our chapter 7 on normal distributions. So we left off talking about the 68, 95, 99.7 rule, and remember as we go through a normal distribution, shown this graph here, 68% of the area under the curve will fall within 1 standard deviation unit of the mean. The 95% will fall under 2 standard deviation units of the mean, and 99.7 will fall under 3 standard deviation units from the mean. So they showed you on one slide, and then here we have another way to look at it, where you have plus or minus 1 standard deviation unit will encompass 68%, and then if you go out 2, it'll encompass 95, and 3 will encompass 99.7. So here's an example of using the 68, 95, 99.7 rule. Here we have an adult intelligence scores are normally distributed with a mean of 100 and a standard deviation of 15. You write that as X is distributed as a normal distribution of a mu equaling 100 or mean and a standard deviation of 15, right? So that's a little different from our binomial distributions where there would be a B in front of it, so the N states that it's normally distributed. And so we would say 68% scores fall within plus or minus 1 standard deviation unit. So if you take the mean plus and minus 1 standard deviation, so plus 100 plus 15 will be 115, 100 minus 15 will be 85. Moving on, 95% of scores would be plus or minus 2 standard deviation units from the mean. So 2 standard deviation units times 15, right? So that's 30, so it would be 100 plus or minus 30, and that will give us between 70 and 130. And 99.7 within 3 standard deviation units, so that'd be between 55 and 145. So next time we can show this, illustrate this a little bit more, as shown here. So here you have our normal distribution scale, right? A bell-shaped curve with our mu being 100 and a standard deviation unit being 15, right? So between here and here, 15 intelligent points on the scale. So 1 standard deviation unit, which will encompass 68%, will be between 85 and 115. 2 standard deviation units will be between 70 and 130. Remember, each one of these is spaced 15 from each other, because that is what the standard deviation unit is, right? It tells us the average around the mean. And then going from 55 to 145, remember that is 3 standard deviation units, now encompass 99.7%. Remember from here to here is another 15 units, which is a standard deviation. So one big part of all of normal distributions is you have to remember the big part of a normal distribution is that the curve is symmetrical, right? So there's symmetry in the tails. And this is going to be true for a normal distribution. And when we think about this, this will help us uncover some maybe secrets that we already kind of knew, or just ways to tackle problems because we know it's symmetrical. And because we know it's symmetrical, we know the total area under the normal curve is going to add to 1, right? So now we're going to start playing with our probability properties or rules, in which we can state, that since the total area under the curve is 1, that, a probability of A is going to be equal 1 minus the complement, that would be the probability A, or if you wanted to find the complement, 1 minus that probability of A will give you the complement of it, and we can start adding in all these different probability rules to it. So if you can determine that the area in their tails is symmetrical, if you had a bell-shaped curve and you went 2 standard deviation units out, right, so let's go back to this example. So if we went out 95%, right, 2 standard deviations out, then we have this part in the tails left over, right? This should include this part here, right? Left over. But if we know 2 standard deviation units out, so this is going to encompass 95%, then we know the total area under there is going to be 100%, right? So we know that there's 2 tails still left. We have this side and we have this side of the tails. And so we know that the total between those 2 tails is going to be 5%, right? Because we have 100 minus 95, it's going to give you your 5% that's left. And since there's 2 tails, if we take 5 divided by 2, we have 2.5. So we know there's 2.5% left on this tail, and then we know there's also 2.5% left on this tail. Remember, because it's symmetrical. So, as it's shown here, because 95% of the curve is plus or minus 2 standard deviation units, we know that 2.5% is in each tail beyond 2.5 standard deviations. So now showing this on a more clean graph here, as you can see, we're 2 standard deviation units out, shown here, which will be this 95% that it's in the total area in the curve, 2 standard deviation units out will be 95%. So we know that there's 5% left over in 2 tails, so one part of the tail is going to be 2.5 and the other part is going to be 2.5 because it is symmetrical. That's what we're showing here. So let's do an example. We have male height. So we have a male height that's approximately normal with a mean of 70 inches and a standard deviation of 2.8 inches. Because of the 68, 95, 99.7 rule, 68% of the population is in range of 70 inches plus or minus 1 standard deviation unit, which is 2.8 inches. So we'd say that 68% of male heights fall approximately between 67.2 to 72.8 inches. Because the total area in the curve adds to 100, 32% are in the tails below 67.2 inches and above 72.8 inches. Remember, if we're only going 1 standard deviation unit at this time, right? So that would encompass 68%. And so there's another 32% that's unaccounted for, and that 32% is in the next part of the tails in half. I'll show you what this means in just a second. So because of the symmetry, half of the 32, 16%, is below the 67.2, and 16% is above 72.8. That's what we're shown here, right? So we had a mean of 70, and then he had a standard deviation unit, plus or minus 1 standard deviation unit of 2.8 inches, and 1 standard deviation will encompass 68% under the curve. So that is this whole area in here. And then so we know that the total area under the curve is 100. And we already know that there's 68% 1 standard deviation unit, so 100 minus 68 is going to give you that 32, right? So the area that's left underneath this curve is 32, but we have 2 tails, so you divide 32 divided by 2, it gives you your 16, and that's where the 16% comes here, and then on the other side here, that is your 16%. Once again, it just has to do with the symmetry, so if you find the value, if you find the value, you know, from area under the curve from the mean and use the 68, 95, 99.7, you can it's going to be symmetrical on each end of the tails. This is also going to be true as we go forward and we start learning that of the different values and the z-scores. So we can the re-expression of non-normal variables. So many biostatistical variables are not normal. We've talked about this before, but we can express non-normal variables with a mathematical transformation to make them more normal. So the examples of how you can make these non-normal variables and re-express them with a mathematical transformation is you would take the transformations of logarithms, right? You have natural logarithms and you have a base 10 logarithm. You can use this in order to re-express non-normal variables. You can use exponents, square roots, and so on. The book talks about this, but we don't go into great length other than knowing that if you want to transform a distribution that's not normal, you can use, most of the time we're going to be using natural logarithms, maybe a base 10 logarithms or exponents, but we don't get into too much more than that. Big things to remember about our normal distributions is remember that there are many normal distributions, right? Anytime a mu or a standard deviation changes, our normal distribution is also going to change. So there's practically infinite number of them because they can always keep changing any little bit, but there is only one standard normal distribution. So 7.2, determining normal probabilities. So since this next part, I'm just going to go over this first part here and then close this video out and then pick the next part up going over the examples of this. So here we have determining normal probability. So determine normal probability when the value doesn't fall directly on 1 standard deviation unit or 2 or 3, right? We don't have an exact if it doesn't fall exactly on there, how do you determine the probabilities and determine the value under the curve? Well, there's a couple things we're going to do for this, and there's going to be 4 steps that we mostly follow. And that's going to be, first, we're going to state the problem. 2, we're going to standardize the value into a z-score, and then sketch the shade of the curve. And then 4th, use table B to determine the probability. So we're going to go through each one of these steps. Step 3 is one that I will show you. Some people will really use it and benefit it. Other people, if you don't need to write it, you don't have to. Once again, I'm not a great drawer, but I will show you how you sketch it and shade the curve, so that way you can practice that and know how well the problem is setting you up. And then at the very end, we're going to be using table B to determine the probability. One way to always remember table B, it starts with the letter B. It's going to be your best friend for the next couple weeks, so make sure you truly understand how to use table B going forward, because everything for the next couple weeks is going to be dependent on table B, so understand that table is going to be crucial going forward. So here's going to be our example problem. If you want, go ahead and try it out if you have the PowerPoint printed. If not, I'm going to pick that up in the next video, where we're going to be going over an example problem, how to determine normal probabilities when we don't have a value falling exactly on a standard deviation unit, plus or minus 1, 2, or 3 under a normal distribution. So we'll be going through all those steps going forward, and I will see you all in the next video.